¿Quieres estar a la última en innovación? Visita www.centrodeinnovacionbbva.com.
So what I will present you today is how we use in-memory data management in our project to acquire data from various technical equipments and to send the data in less than a second then to our client here. So this, it's slowly coming. Okay. Right. All right. So the talk is about high availability platform for large infrastructure monitoring. And this is called C2MON. This is the project that I'm working on. So as I already said, it's going to be about in-memory data management. But before diving into that topic, I would like just in general show you how we treat the big chunk of data, the physics data. And I want first to show you a bit which kind of data we have at CERN. So of course, the biggest part are the physics data. And there we have already stored more than 100 petabytes of data. So some people still don't know what petabyte is, so it's what comes after terabyte. Yeah. And but we have also a part of that log data, configuration data, metadata of the and what we are treating is then sensor data of technical installation. So you can think of temperature sensors, of field state of tanks, of security doors. So everything what is interesting to monitor the big accelerator, the LHC. So you can divide these different kind of data in data at rest, how you call it. So data that you don't need to analyze directly. You would rather store them somewhere and later do analytics. So this is what traditionally we are doing with a relational database, or nowadays for big data with things like Hadoop. And then you have data in motion. These are data which you have to analyze as they arrive in real time. And I will show you later techniques how you can do these kind of things. So first, some words about CERN. CERN has been funded in 1954. This is already more than 60 years ago and was a very early stage, and it was even before the foundation of the European Economic Community, which was in 1957. And we have now 21 member states from Europe. The only one which is not from Europe is Israel, who joined last year. And in total, we have 10,000 scientists working daily at CERN, from which we have 3,300 staff people, and the other ones come then from universities and partner institutes to work then with the machine. So we are like a big service provider. We don't do physical fundamental research as such at CERN. We have only one theoretical physicist employed by CERN, or two, and the rest are coming from outside. So it's more a service provider. And so our budget, our yearly budget is about 1 million Swiss francs, which is almost 1-to-1 to euro now. And so you might ask yourself, so is it worth to spend so much money in fundamental research? And from my perspective, I can say yes, because you never know. That's how research works. I mean, you research and you don't know where your journey is ending. But all along the way, since you're always working on the limit, you will find out new things. So what was invented at CERN is, for instance, the World Wide Web protocol by Tim Berners-Lee, which we all use now daily. But also, just because we do particle detection, and so this is now used in medicine a lot. So for instance, computer tomography is something that came out of research made at CERN. Or now we have like 40 Hadron centers around the world to treat cancers. And basically, we are a big Hadron collider. Yeah? So out of this, there's already investment for the industry. So another thing is that we are leading in grid computing, and we also started an open hardware can download the blueprints from hardware pieces and then just start the business out of that. But what is exactly going on at CERN? So CERN has the biggest machine in the world, which is called the Large Hadron Collider, and it's a big accelerator which sits 100 meters under the surface, and which is a ring of 27 kilometers in circumference. And then the collisions actually take place in 4 big detectors, which are ATLAS, CMS, ALICE, and LHCb, from which ATLAS and CMS are general purpose detectors to just study the nature of particles. So what we accelerate are protons, and then what was the latest discovery, or the biggest one, was in 2012, what is called the God particle, the Higgs boson, which gives every other particles their mass. So this is how the theory describes it. And yeah, but what you can also then study is dark matter, and we are also doing research in antimatter. So all that together produces a lot of data. So you've seen in the previous slide we have 100 petabyte already stored at CERN. And so now in 2012 we were running the LHC with 3.5 tera electron volt. This is not for not very speaking, but there was a technical, and now we just started again a machine, and from next year on we expect that we can double energy, which means also doubling the amount of data, you can say. Yeah, and so this is run 2, and then there's planned in several years to have another technical stop and run 3 to even upgrade more the machine. So also our data rate is increasing like in every other business. So just to look a bit into the most interesting, is the biggest particle detector. It's ATLAS, so he's really big. I mean, he's 46 meters high. You have to imagine he sits 100 meters under the ground, so there's a big hall. Then you go down, you cannot imagine that you're so deep under the earth. And he has 100 million channels, which means 100 million channels that can send data, that can detect something. Yeah, and collision rate of 40 megahertz, which means around 100 petabytes a second. So what are you doing with all this data? Well, nobody can treat that at the moment. So what we do is we have a 3-tier filtering, the hardware filtering, which already goes away most of the collision, either because the events that are created are already known or not interesting, so because you want then just to filter out what is new, what is interesting. So after this hardware filtering, and then we have 2 software filters where you go then a bit more in deep and try to analyze it, you end up with a rate of still 200 events per second, which is about 320 megaseconds. And just from Atlas. So then there are the other 3 experiments, and all that has to be stored somewhere, yeah? And it's constantly coming, this rate. So we're talking about peaks. I will show you that in the next slide. First of all, we don't have not only one accelerator. No, we have 9 accelerators, and they are all like connected together. So nothing is thrown away at CERN. So from the beginning, they started with a small one, with 2 meters of diameter, and then the next one. And if you like, it starts from a little hydrogen bottle, and we extract the protons, and then they go to the first ring. We try to give them the maximum energy what the ring can do. Then it goes to the next and to the next, and until it arrives to the big LHC where the collision takes place. Also called the Lord of the Rings. So what do you think? Where do we store this data? You think we use Hadoop for that? I mean, 100 petabytes, 30 petabytes a year. So I have to apologize. Unfortunately, we don't use this latest technology. We use still tapes. So why that? But first, we use Hadoop at CERN, but it's only for the metadata of the physics data, so that you know from which trigger the event is coming from. So this is stored into Hadoop store. So in run 1, which was until 2012, we had 30 petabytes per year, and this demands a lot of processors. So we have the grid computing, which does then this filtering, and then has to send the data to the tape library, and then it has to be flushed into on tapes and on a really high rate, and so we have peaks of 20 gigabytes of seconds that we have to cope, and there you need a real-time system, because if you miss 1 second, next second you have 40 gigabytes to store, yeah? And this is our precious God. I mean, we don't want to lose any. I mean, this is our work, yeah, our daily business. So we have 80 tape drives, and for the run 2, we expect like 50 petabytes per year. And so currently we have freed 150 petabytes in our tape storage to be prepared. So what we have to do, things like defragmentation of tapes is a big thing, that when things get deleted, you have again to clean up the tapes so that you constantly are able to store all the data with the same amount of tape, because we don't want to add a new tape storage every year. Yeah? So we play with Moore's law, that the density every 2 years doubles. And IBM now just announced that they are able now to store 220 terabytes on one tape, which is enormous. At the moment, I think what you can buy is like 60 terabyte for one tape. That's the maximum. But we see that there are ways in the future to keep on with that bet against Moore's law. Right, and why tape storage and not disk storage, you might ask? They are slow in reading and all that. Well, but they are really fast in writing, and we don't need the physics data straight after they have been collected. Normally, it's then a physicist that comes after 2 months with his cup of coffee in his. Okay, now I need that data. So he can wait for, let's say, 10 minutes before he gets his chunk out of. So we have like a disk pool where we put the hottest data in, but then it's on tape. Yeah, and of course the cost of a tape is much less than disk storage, and there's no electricity consumption if nobody uses the data. Yeah, and when you compare to Hadoop, normally for tape they're very reliable, so it's enough to have one copy of the data. When you're in Hadoop, you normally make 2 copies. So it already, when you have 100 petabytes, you have then 300 petabytes. Yeah. So thinking of that, it's wiser to use tapes. So for what do we use Hadoop? Or at CERN, we do it differently. We have what we call an age-based service. Since it sounds like we are a lot of people, 10,000, but the core staff members are really few people, and we have to deliver a lot of services to the physicists. So, for instance, for our age-based cluster, I think we have like 3 persons which are responsible for that. Yes, and so what CERN does then is trying to build up services, main services, then the different clients, they can use it in different ways. So there is then this age-based cluster, and currently it's used by 3 bigger projects. So one is called the Castor cluster, which is Castor is the project that the data to tape. Yeah, so there is a custom in-house solution for that, and what they store there is their log data to make analysis of where which file got on which tape and so on. And then there is the Atlas cluster, which is the event index catalog for the metadata, and a monitoring cluster to store all the log events coming from the computer center. So just to give you an example, what we store on this tape storage is then on which tape is my file stored, is there a copy on disk, things like that. This is the metadata. Yes, and at the end, you can really trace it from a web page. You can say, okay, I want really to see the full history of one file, or things like that. I mean, it is more for experts then. And here I just showed you that it's really fast coming out. So we'll read it. It's 0.11 second it took then to do the query against the HBase. I mean, which requires, of course, also a good network infrastructure, good servers, and so on. Right, the other example is then this metadata for the physics events. So there you store information about event number, run number, timestamp, luminosity. This is how many collisions were per second. Things like that are interesting. And yeah, so what they did is before we had already a solution ready in the years 2000, let's say. And at that time, Hadoop didn't exist. So what did we use? Well, we used traditional relational databases for that. And but this doesn't scale anymore for us. So now for the run 2, we have put in place a new solution then based on this HBase cluster. And what we use to send the data are ActiveMQ brokers, which are JMS brokers. And they can, I wrote it here, they can handle peaks of 200 kilohertz. So they're quite reliable. Yeah? And it's open source software. So this is also always interesting for us. So, and then, I mean, there's like a buffer which like buffers first in memory events that's coming from the same trigger. It's stored into HDFS. So then later on, they are interested, for instance, in questions like, give me the reference to this event in that format for given process cycles, things like that. And then like that, they can already like try to find like events that belongs together to the same collision. All right, so there's a lot of research going on around big data at CERN, but I mean, when you run a service, you cannot change overnight things and running projects, and and because we have to keep on going the service, and so you cannot jump just on the newest technology. But there's a lot going on, and in the future we will more and more go towards NoSQL solutions. At the moment, it's still the biggest part of data are still in relational databases, and there must be a change of thinking, because it's now the time that big data became mainstream. Yeah, and so there's things going around Oracle DB to put things in Hadoop and combine them with the R protocol, so R scripting, and this is for advanced analytics. And there's a nice introduction, which is this swirl to learn R. And another thing, what we are trying to look on is complex event processing, which I will explain you in a few minutes. So all these are technologies to put data in memory. So before I will now go into my project, I want just to quickly introduce you to what in-memory data management is and for what you would use it. So when you look again on the data, it's more, in our case, about sensor data, which we have to analyze in real time to then trigger alarms or events based on the incoming data stream. So what we have seen in the past is really a growth of data. So everything becomes bigger, and so you have more transactions, more sensor data, logs coming around. And what matters in the industry, as for us, is the latency. So how you get the result. Nobody wants it forever in front of a web page, just that it appears. I mean, we are now used that everything goes quick, and we get really annoyed if something is not working as fast as we expected. So and it's also I mean, time is money. Yeah. So what in-memory helps you as well is if you have really, for instance, we had 24/7 service, and for us, we use it, for instance, for be as independent as possible from third-party products. Like a database needs to be patched, it needs to be sometimes fixed, so it's not always available, but we have to be available. So we put things in memory just to realize also high availability and to meet our service level agreements. And what we see is a shift. We see a shift from data which is traditionally stored in normal disks to a shift into RAM. Yeah. So normally, what 90% of our data are on disk, but in the future will be maybe more the opposite. We will have 90% on flash disks or directly in RAM. Now, because there's this steep drop in price in RAM, it became so cheap nowadays. And on the other side, we see an explosion in the volume and velocity. So in-memory data platforms are on the scale of NoSQL, but with a much lower latency, because, I mean, there's nothing faster than having already your data in RAM. Yeah? And it's nowadays the products which are offered on the market are very reliable and fault tolerance and guarantees also transactions. So you can talk about big fast data when talking about in-memory management. So just to show you a picture, normally when you have something in, you speak about seconds to get something out, and normally it has to be transported via the network. There's the next level, which is the distributed memory, which can sit either in the server RAM or flash disks, but still are not on your machine, but in the network. So it's like a shared memory. Or you can have a local off-heap. So I'm now talking here more about Java projects, because they have their garbage collected data, which is the process memory. And normally in Java you don't go over 4 or 6 gigabytes, because then the garbage collector cycle will take longer and interrupts you the full process for several seconds, and can be even 15 seconds or something like that, and you don't want that. Yeah, and there are these off-heap stores now, which are outside of your garbage collector cycle, and like that you're in control of when you want to delete, and doesn't give you this unpredictable interrupts. So here it's an example of from the product that we use. It's from Terracotta. So you can scale it up if you want, and scale out on your needs. So at the beginning, maybe a huge database, and in the second step, you would put more data from your database in big memory. And as your business grows and you see maybe you need more and more faster data, you would put more and more things into big memory, and then you can scale out. If it doesn't fit anymore into one single machine in all your RAM, it allows you to distribute it in multi-machines, and still that every client connected to this shared memory will have always the latest data. And this is then, and he will only keep his local memory on the machine the hottest data, if you like. So that is elastic scale. Another thing that I would like to show you is, so how do you, this is like storing, but how do you analyze data in motion? And there an interesting technique is the complex event processing, or called CEP. So imagine that you have events coming from different type of data. I mean, apple beans, you cannot really compare them, but what a CEP engine can do for you, it's like a SQL query, but in real time. Yeah, so things go through, and so for instance, for us, it's interesting to also see if an event hasn't come through. Yeah, so at the end you can trigger actions of that, and your data has to be, I mean, CEP used then in Inmemory Stake to build up a history you want to look over time. So this technology is influence a lot also the industry nowadays. I mean, a big user of in-memory is, for instance, PayPal. They have a lot just on flash or in memory, and everywhere where you want to deliver fastly your data to your client. So I have 5 minutes left, I've heard. So we'll quickly now just show you how we do it in our project. So we get data from access control, safety systems, electricity data, cooling, cryogenic. So these are our sensors, and we have between 90 and 100,000 sensors. And what we have built up is a platform called Controls and Monitoring Platform, because we have many monitoring projects at CERN, and everybody, well, in the past tried to reinvent the wheel, and we said, well, at the end, everybody has to acquire data. They have to store the data somewhere, and you want to send them reliably to your client tier. And all these core functionalities we try to put into one solution. And then at the moment we have 2 big projects using it. One is ours, TIM, for the technical infrastructure monitoring, and Diamond is more to survey a big farm of computers. That's just a little joke. I don't know if you know what DQ would mean, but we try to do, normally you get raw data in, so garbage in, quality out. So we try to do a lot of filtering before we store the data, because a lot of sensors they come from analog sensors, so they send either too frequent updates or not really important for the business. So we try to filter all that out with a fine-tuned filtering strategy, and at the end we can throw away 99% of our data, of the raw data, without losing any information. Yeah. So this is just the insight. I mean, we'll not go in details, but in fact we have like a server core which is then built around an in-memory store. And nowadays in Java there's a standard called JCache, which is part of Java, and which allows you then, and then now there are different vendors which have implemented their in-memory solution against the JCache standard, which makes it easy for you then later to switch from one product to the next without changing your core. Like, okay, I said already all that we are 24/7 service operating since 2005, and we are used by the technical infrastructure operators in the main control room, and they have like synoptic displays. And so we have 400 million raw data values, and we filter out and end up with 2 million updates that we send to our business tier, where we have then 40,000 alarm defined, manually alarms defined, and this is our business logic, and then alarms can be triggered and have to be sent to the client tier, to the operators, and they would then call the expert, or will look on their synoptic displays, or for instance we have applications on top to handle the access to the tunnels, and so on and so forth. Right, how does it look just from the setup? So this is the setup which we use for TIM. It's we have these data acquisition processes, which are individual Java processes acquiring the data from the different technical equipments, and they send through JMS brokers the data then to our C2MON servers, which will store the data into the Terracotta store. And he will also do a backup still on disk for emergency recovery. But Terracotta also allows you to do that, well, by configuration, but we didn't want to be too dependent on one product. Well, and then once the data is in cache, we send it to our client here. And all that happens within less than a second from the source to the client. Then if you one day, if we have higher requirements and we have to scale, this will be easy, because we will just add more servers, and we will scale out our server array. And what we find, I mean, maybe the biggest advantage of all that technology is that before we had a single server when we started in 2005, and was at that time G2EE application server, but it didn't work out for us, because we have a high write input and very low read output, and G2E was more the other way around. Nowadays we use Spring, which is an open source framework. We use Terracotta, and what we can do now, just having two servers running, is making rolling updates. So we one, patch the other without bringing the service down, and like that we achieve high availability. And we just have set up like 2 times a year, like a space for allowing really downtime for our service in case we have updates which are not compatible anymore to the store. That's mainly when you change your object that you keep in the store, when you change namings and so on. Right, this is a bit the roadmap. So we will invest now in complex event processing this year. We have students which will start with that, and because we had our own rule engine for the moment, but it doesn't fit anymore the requirements of today. And so interesting, there's an open source project called Asper, which is providing you a CP engine which for open source. And we're also looking into time series databases, because our data are all more time related, and at the moment we still use relational database for our short-term log, but then to get data out, it's becoming really slow and painful. So this is for us the future. one very interesting is InfluxDB because it's recent, but it's like a very native time series database and optimized for this. So you can directly get averages out of the database. So yeah, worth looking. But for us also would be TSDB, sorry, because we could just be sitting on our H-based service. So we have it already at CERN. So for us, it would be just starting this called TSD servers and sending them our data. We could profit already from existing infrastructures. Right, takeaways. Just so data and high availability services are more important than ever before for all modern organizations. And everybody wants to derive more value from the collected data. And this is to success for many for all companies. So in-memory data platforms will play a bigger role in the future, and already now, because they can deliver really fast your data. So this is just to thank people from CERN and people from Software AG, where we work close together. And you will find also the references to other presentations around that topic. And I would like to say muchas gracias por su atención.